So here's what we're talking about. Topic 14. It's a pretty short topic. We dealt with digital and digital versus analog signals last time, and how to store digital signals and why we use digital information as opposed to analog information. Today we're going into a very specific device, which has really changed our understanding of the universe in a lot of ways, which is called a charge-coupled device, or a CCD. They do make X-ray CCDs now, which we'll talk about. A CCD is it's digital camera. That's what it is, basically. Okay, it's how a digital camera works. Okay, so we need to understand what capacitance is. We need to understand the basic operation of a CCD, define quantum efficiency, magnification, resolution, solve problems, and name applications. So we'll do all that right now. Okay, start with a capacitor. If I take two conductors, and generally we think of them as being like conducting plates, and they are separated by an insulator. There's an insulator in between them. We call that a capacitor. It's pretty simple, pretty simple. Two conductors with an insulation in between them is called a capacitor. And there's a variety of kinds of them. We use them in almost every electronic device these days. But if you take a capacitor, if you take these two insulators and put them into a circuit, okay, hook them up to a source of potential difference, like a battery or something like that, current will flow very quickly, and charge will build up on those plates. Opposite charges will build up because they'll be attracted to one another. The electrons will try to flow in the circuit. They'll hit this barrier where the insulator is, and you'll end up with a positive plate and a negative plate. A potential difference will build up. And basically, that capacitor stores electricity. It stores that charge until you need to do something with it. Okay? It's kind of like it can be used kind of like a battery in some ways. And in the transformer itself, I'm not sure if there's a capacitor, but yes, in alternating circuits, they can use capacitors to weed out DC and make sure that it is just alternating that's getting through. That's one use of them. Well, for like televisions, yeah, a lot of devices that have capacitors, they can potentially store a really high voltage even after you've unplugged the device. And that's why it can be really dangerous to take apart a television, for example, because if you touch a capacitor that's charged, it can kill you. I mean, if it's a high enough charged capacitor, it can be a really big shot. The math with capacitor is pretty easy. This idea of capacitance is how much charge it takes per potential difference that gets created. That's kind of the idea, and yeah, it's charge per volts. That's how you would calculate capacitance if you needed to. Coulomb is charge. So like it's how much charge it takes to get how much voltage, basically, is known as capacitance. Coulombs per volt. And technically, that's a farad. The unit of capacitance is the farad, named after Michael Faraday. And a capacitance of 1 farad is actually very significant. That would cause quite a painful shock in you if you were to touch a capacitor that had built up that much capacitance. It would be tough. Let me show you kind of a picture, because I'm telling you all these words, and it gets kind of confusing. I think the picture makes a little more sense. But some of you are still writing, so I will wait. Here's what they look like. They come in all shapes and sizes. Notice they can be really tiny. Sometimes they can be pretty darn big if they are holding a lot of charge. Here's the idea in a circuit. Let me show you this little circuit diagram right down here. Okay? Notice that I have a capacitor, and I have a resistor, and I have a source of potential difference. That could be a battery or it could be an outlet. I'm pretty sure this is right. Double check with me on that, right? Positive and negative terminal, the way that's drawn. I think that's how we draw them. So imagine what happens here. When I close this switch, for a moment, okay, the electrons are going to want to flow. But remember, we draw current going the other direction. We draw it going from positive to negative, but we know it's the electrons that are moving. So what will happen is you'll get a negative build up here and a positive build up here. And they'll be attracted to each other, right? They want to discharge. There's an electric field generated in there. And it's like, oh, those things, they want to get to one another, but they can't because there's an insulator in between them. And that's capacitance. And then if you do something, you can either discharge that capacitor or it does a variety of other things in the circuit. That's all a capacitor is, okay? It'll hold a charge. It doesn't. It flows for a minute until the capacitance builds up, and then it stops. By the way, you guys, another word for insulator is dielectric. I don't think IB is going to use that on you, but if you start looking at capacitors, they'll talk about a dielectric in there. And what that means is there's an insulator in there. Now, here's the deal. In a CCD, in a charge-coupled device, basically, it's a grid of millions of little tiny capacitors. Okay? It's like a chessboard. or checkers if you're not that adept at chess. Same board, right? Bunch of little squares, okay? Um, this thing was invented in 1969. The people that helped invent it won Nobel Prizes, so this has been a big deal. I think there's been 2 Nobel Prizes given out in the realm of CCDs for physics. And the purpose of a CCD is to take very high quality, high resolution images. Digitally, okay? Exactly. This is a digital way of taking images. And basically what you get is you have this grid of, we're talking about millions of them this time, of little capacitors. Okay, exactly. A pixel, you guys have heard of megapixels and stuff on your cameras and things. A pixel is one of the little squares, one of the little squares on your chessboard. Okay, one of those little capacitors is called a pixel. So if you have a 6 megapixel camera, it's got a CCD in there that has 6 million little squares on its CCD, all right? And each of the little squares is a capacitor, and it can store electric charge. And what happens is when a photon hits a pixel, okay, the photoelectric effect, remember this from when we were dealing with the photoelectric effect in quantum mechanics, right? When a photon hits that pixel, it knocks off an electron, and that little capacitor stores that charge. Cool. And it'll hold it until you do something with it, right? Okay. You with me so far? The voltage that gets created in each capacitor, okay, is equal to the charge per coulomb. Wait a minute. No, the charge over the capacitance, sorry. So the amount of charge, basically there's a relationship between either the number of photons or the strength of that photon that hits that pixel will determine how much voltage you get across that little capacitor. So the potential difference that gets created in each little pixel is proportional to the number of photons or the intensity of light that hits that pixel. And it can be measured. Suddenly you have a voltage that tells you exactly how many photons hit that one little square of your CCD. Okay? And you can record that information digitally, and therefore you can record that image. Because if you have lots of little squares, you've got lots of photons hitting it, different intensities, different amounts of photons. Each little pixel will have a different voltage. Okay? So the pixels are organized in rows and columns, right? Okay? The potential of each pixel is shifted downward. Okay? So imagine you have your chessboard here, and you open up your shutter so that each pixel receives some light, and voltages are recorded. And then what happens is, in order to store that information, you shift all of them down one so that the information goes into this, from the bottom row, goes into this very bottom row. You know what I mean? And then, I'll show you. And then it's measured and recorded and can be reduced. So what happens is you shift the information down to this bottom row, and then one at a time, you shift this bottom row's information over to the right. You amplify it, and then you store it. And so it says, this first pixel is 3, and this next one is 4, and the next one is 3, and the next one is 0. And you store that information. Once you've stored that whole row, then you shift them all down again. And you store the next row. And you shift them all down and store the next. And by that, it stores the whole grid information in a string of binary numbers. And it knows which pixel is located and the strength of the voltage of that particular pixel, and it can reproduce it. Yeah, but then that's stored in binary code, let's say, for example. Like, let's say it was 3 volts and 4 volts. Yeah, okay. 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 So now colored images, if you have a colored, what I talked about makes some sense if you think black and white. Color, it's exactly the same, except for instead of just having black and white pixels, you have color pixels all together, and they work in groups of 4. Every group of 4 pixels, you'll have 2 green, a red, and a blue. And again, you can measure the intensity of those particular filtered colors of light hitting it, and then by reproducing the intensity of red, blue, and green, you can produce every color in the imaginable universe, and that's what we see. I'm going to show you, again, a diagram of this, and it'll make a little more sense, okay? I've seen this whole yellow thing, and I don't know if it's just a marketing ploy or not.
Probably.
Might be.
Samsung is
okay. So here's your CCD. Okay, each of these little squares is a pixel. A photon hits that pixel, it's a capacitor. A certain voltage will be created on that pixel that will be an indication of the intensity of that photon. Yeah? Okay. Well, remember the photoelectric effect. The photon comes in, boom, knocks it off. It's kind of like the battery. But so then all that information is stored here. You open your shutter, bling, for a second, you close it, boom, and then all that information is stored here as voltages for each pixel. Good so far?
Yes, sir.
Okay. Then down here is where that information gets stored. This is called, the bottom row down here is basically is not part of the CCD, but you take all the information, you shift everything down one row, and then you take the voltages of each pixel and you move them through this amplifier and you store that information digitally. Like, okay, pixel number 1 had this many volts. Move pixel number 2, this many. Pixel number 3, and once you've done this whole row, then you shift them all down again and do the next row and the next row, and then it does it really fast because it's a computer. You know, these things are fast. Okay. Now, and again, what I was explaining with a so does how a CCD takes information from light, the intensity of light, and turns that into digital information, does that kind of make sense? Yeah. Okay, more or less, right? So the idea being, if I open my shutter and here's you, right? That light from you is going to be more intense in some places and less intense in others. It's going to affect each pixel differently, and that can be stored as a voltage, which can be stored as a piece of information. Okay? Right. Oh, the little, yeah, that's good. Those little metal needle things where you can, it's kind of like that. Okay? And then basically you just, guys, and then you just organize that information one pixel at a time, and you have a little memory chip in there that remembers it one pixel at a time. Okay? Craziness. Now, what I was trying to explain with a color image, it's exactly the same, except for the pixels work in groups of 4 with 2 greens and a red and a blue. The reason there's 2 greens is because green wavelength evidently is the wavelength of light that your eye is most sensitive to, and so it's has the greatest effect on the color of an image. So I guess that's why they do 2 greens to a blue and a red. But you're right, there is a company out there that's now doing, one of them is yellow. They do a yellow, green, red, and a blue, and I don't know if that actually really makes a difference or not. Because in terms of color, you think of color in art class, we always talked about red, blue, and yellow being the primary colors, and that's true for pigments, but for light, it's actually the opposite. It's actually magenta, cyan, and I forget what they call it, but it's red, green, and blue are basically the additive colors of light that produce all the other colors. Okay? Things. Quantum efficiency. Quantum efficiency. Sounds pretty cool, doesn't it? It's awesome. No. The quantum efficiency of a pixel is basically the number of electrons that get ejected divided by the number of photons that are hitting it. So if you have really high efficiency, you'll get the same number of electrons as you got photons. That'd be 100% efficient, right? Okay? Because think about it, some photons bounce off the device, some photons will pass right through, and so you can rate the efficiency. A CCD happens to be pretty darn efficient. They tend to be about 70 to 80% efficient, okay? Back in the old days when we used film to take pictures of things, it was much less efficient. Photographic film was like 4%, okay? Most of the photons bounced right off and didn't cause a chemical reaction. The human eye is 1%. Think about that. Most of the photons going into your eye aren't causing the cells in your retina to do anything. 99% of them are just bouncing around and coming back out and nothing. So a CCD is much more sensitive to the photons than your eyeball is. Brian. Okay. So let's see what else we got here. Yeah. I'm not sure what it would look like if I... Yeah, I don't know. That's a good question. I don't know. Okay. So here's the deal. So we can use CCDs. Remember when we talked in astrophysics how we can measure the brightness of stars and compare that to how bright they should be and things like that? This is how we measure the brightness of stars. You can very precisely, with a telescope with a CCD, you can very precisely measure the number of photons that are hitting per unit area. You can measure the brightness of an object very, very accurately, okay? That's the actual brightness. Right. Right. Okay. And if you know its luminosity and you measure its brightness, you can measure its distance. Remember, that was one of the techniques. So this is how we measure the brightness of objects. More efficiency, Rex, this kind of goes into your question. More efficiency means you can do an image either more rapidly or with less light. So I don't know for us, if our eyes were more efficient, we could probably see in the dark better, for one. But I don't know what it would do, like if we'd see things in more detail. I don't know. It's a good question.
I think we might register. Oh, you can have Twitter.
Yeah.
You'd be able to like follow
Okay. Now I just want you to see something here. I decided. Now the Hubble Space Telescope has a CCD on it. Most modern telescopes, modern optical telescopes, there's not astronomers sitting there looking at them with their eye. Okay? Okay. Hold on, I want to get everyone. Modern optical telescopes don't have an eyepiece. They have a CCD. Okay? This is the Hubble Space Telescope. This is an image from it. It is freaking incredible. And the Hubble Space Telescope has a CCD on it, so it can sit there and look at something in space. It'll register that image, download it to some computer here on Earth, and we get it. Now, this is some nebula out there. It might be the Eagle Nebula. I'm not sure, but look at that picture. That's pretty darn amazing. Now, if we took a telescope, same size and everything, stuck it out there, you know, and looked at it with our eyeballs, okay, our eyeballs, this is what it would look like. Pretty awesome, huh? Okay, that's the difference, okay? That's the difference. CCD, much more efficient. It can register things that are so faint that our eyes just would never see them. And think about this. Your brain is processing images about 60 times a second, okay? A telescope, so that means that when you look at through a telescope, you look at anything, you receive photons for a 60th of a second when your brain says that's what it looks like. Whereas a telescope with a CCD, you can open up that shutter and just let it sit there for hours or weeks and let photons hit that CCD over and over and over. And that way you can image things that are so faint we would never see them with the naked eye or with even the eye with a telescope. You just can't do it. But a CCD can record those things. Okay, thanks. Okay. Other things we can do. Other characteristics. Okay. You can magnify. Ooh. There we go. And we want to talk magnification and resolution. Magnification is pretty darn easy. If you have an image, you know the size of the image, you divide that by the size of the actual thing, that's magnification. Pretty easy. We can either magnify bigger or magnify smaller, depending on what we're trying to do. Resolution is a pretty critical thing in imaging when you're trying to image either something that's incredibly small or something that's incredibly far away. And the idea of resolution is if two things are actually separate, if you see them as being separate, you have resolved them. If they look like one thing to you, then it's not resolved. Does that make sense? So imagine two really close stars really far away. If you see them as one dot, one star, you have not resolved them. Like Alcor and Mizar, exactly. If you see them as two, then that image is resolved. And in terms of technology, what that means, and there's a lot of math that has to do with like opening of an aperture and stuff like that, whether or not something can be resolved. But in terms of a CCD, if two objects fall on two separate pixels, we can say they're resolved. But actually, if those two pixels are right next to each other, that's not good enough. So what they say is they want them to be 2 pixels apart. If an image is 2 pixels apart, we can say that it has been resolved. So more pixels is higher resolution. You can resolve things better with more pixelation. Here we go. Some other uses of CCDs. Obviously, CCDs were revolutionary in the world of astrophysics and modern culture. Think about your cell phones and your cameras. Every one of them's got a little CCD in there. It's crazy. Okay. I mean, where would Facebook be without the invention of the CCD? Yo, we can make a little rap. Okay.
Yeah, it was recorded.
Okay. Nice. Okay. Here are some other uses of CCDs that have been extremely helpful. One is called endoscopy, which is basically taking a little camera and sticking it inside of someone's body to look at things. Okay? Since we can make these cameras so small, we can now, mainly they do it, fiber optic. Mainly they use endoscopy in the digestive system, so they can actually send a camera kind of down your throat into your stomach or in your intestines. They can go up the other entrance and look at things.
That's not an entrance.
And the other exit, sorry. The other aperture is what I meant to say. But this technology has been super helpful in medical. And I actually went on the internet yesterday. I was gonna show you an image, but they're really gross. So I didn't put one on there. But you can check it out if you want. But you can actually take a camera into a person that's alive and like look inside of them and see if there's things wrong with like their cell linings of their intestines, or you can look for cancers or things. It's really and actually there's surgeries now that can happen that are so much less invasive because the doctor doesn't have to actually be able to see what they're cutting off. They can stick the camera in there and then they play this little video game with this little thing and they cut you open and do the stuff.
There was a heart surgery that
Yeah, yeah. And Tyler, you had one too? The other thing that currently is with CCDs, and this is something you guys were alluding to with that Hubble picture, is they have in fact developed X-ray CCDs. Okay, they've developed a charge coupled device that is sensitive to X-rays. And think about, I don't know if you guys noticed, but like your dentist, or at least my dentist. I go to the dentist and it's like, oh, got time to take an X-ray. And he sticks that thing in my mouth, and it's so painful, and I hate it. And he pulls that little thing up and goes, nee. And then boom, there's the picture right there on the computer. That's because he's using a CCD. There's no more film involved with X-rays if you have that technology. And the thing that's awesome about that is the CCD is so much more sensitive than X-ray film was that you can get an image with much less exposure to the X-rays, which is great for us, right? You don't have as much lower risk of cancer because you can get the X-ray image with a much lower dose of X-rays. And you get the image instantaneously. You don't have to go develop it and do all that other stuff. So it's kind of cool.